Let's now understand how artificial neural networks work. They are also called feedforward neural networks in their vanilla form. That is a form that isn't modified, such as what we will learn below. First, the artificial neuron is inspired from the biological neuron. Here's a neuron, and normally it accepts information through its dendrites, and it processes it, and at some point, when the electric charge it gathers reach a certain threshold, then the neuron emits a spike through its axon, which is itself connected then to another neuron in another layer of neuron. So here also it's worthy to note that when the neuron captures information, then it retains the charge for some time, and this charge is exponentially decaying over time towards zero. So if there are enough stimuli sent within a short time frame, the neuron will fire if it reaches its firing threshold, which can be called an activation function. The artificial neuron, inspired from the biological one, is quite similar. So we have many inputs, for instance here n number x. So it's a vector of x, and it contains floating points, just for instance values between -1 and 1, and the neuron will, through its kind of dendrites, here we call them weights. The weights will weight the information we receive, such as to negate it, or to multiply it by 0 such that we ignore it, or it can positively or negatively weight the information inside the neuron. So we do a sum of two weighted inputs. So for every input I here from 1 to n, we will get the weight times the input, and we will finally add a bias after the sum. So this bias here is another parameter that is learned. So the weights are learnable, and the bias is also learnable. It can do an offset in the learning such that we can have more complex behavior that is being modeled. Finally, there is an activation function here. However, it doesn't work exactly like the biological neuron. So here it was only a threshold. If the value is above a certain threshold value, then we send the fire signal, or something very similar to that, to be precise. It's not exactly that, but we can summarize it like that. So what we do here with the activation function is that we kind of clamp the information of the neuron between some reasonable values before outputting them. But more importantly, this activation function is not linear. So this is to counter the fact that here there was time. We could wait for inputs through time, and then if it was above a threshold, then fire. Here there is no notion of time. We just happen to have a vector x in input. We wait every f2s, we sum, we do something, and there is no decay of the information in the weighting of the arrival of it. So the activation function is not like if it's above something fire. It's more like it's like if we did the integral of this over time a little bit. So we will see a few of those functions later, but it limits the range, and it is a non-linearity. Neural networks, artificial neural networks, are composed of many artificial neurons. So we have inputs. Those can be like perceptrons, they are called. Those can be literally data. So we feed in values of luminosity in pixels, like for image classification, or we can send in some signals that are read from sensors, things like that. Then we have hidden layers, and those are just regular layers of neurons here. This is a feedforward fully connected layer. So it means that every neuron here is connected to every of the previous neurons and only the previous ones, so that we can compute the information from the left to the right. We could do it by hand, and there is no notion of time in that. So it's called hidden just because it's not at the output, and we don't really observe them. We train them, but we only observe them for debugging them, or sometimes to do some fancy experimentations or things, such as, for instance, Spotify. A Spotify intern once did a neural network where if we selected a few neurons, they could generate playlist with this neuron detecting, for instance, Chinese pop. So the output layer is what we're really interested in. We see here 3 outputs. So we could be classifying signals that we receive within 3 categories, such as is something in some state or the other state or in another state. So we can predict what we see right now. So this can act as a function because in fact this neuron will output a value through its axon at the end, which we can read as an output. So we can do with that a regression. This means we would remove the activation function at the end temporarily, so that we can have values that range from -infinity to +infinity instead of values being clamped to some like restricted domain or image. So this here would be a regression. So we can predict from data one or many sliders, so values to do regression on. Classification is different. So here, as we have 3 neurons to do classification, what we would do is simply to pick the one at the end that has the highest value predicted from the data. So the highest value would represent that, okay, this neuron is the one that is the most activated. And as we would have trained the neural network with some of those final neurons being assigned some categories. For instance, we see an image, is it a cat, a dog, or a giraffe? So by training the neural network to generate outputs like those, then in inference prediction mode, we can pick the max and see what is the category. So here we have 2 perceptrons that can receive data. Let's say that we do a chart of this at the right. Here's an image from scikit-learn, from the scikit-learn documentation website. So one of the neurons could vary here between 4 and 8, and another one could vary between 1 and 5, for instance. So we have many data points, and for each data point we can pass it through the neural network to get a prediction. So we do it and we get the class that has the maximal value, and we color the chart accordingly. We could get a result like that for trying every point. So here's a nice colored chart for classification. So a neural network is like an universal function that can learn almost anything from data, as long as it's trained on enough data, and that the data has enough signal to do the prediction. For instance, a human could do it with the same data, and also it needs to be trained long enough and to have enough neurons for the task. For sure, if you want to generate language, you will need a lot of neurons, much more than that. So it depends on the task. The learning process, which is most used, is the supervised learning process. So we take inputs, we feed them into the neural network, we compute the outputs by simply doing the math. And notice that here we already have some weights between the neurons. Those weights are pre-initialized with random values most of the time. So those values are often picked from distributions, for instance, a normal distribution or a Gaussian, same thing, or a uniform distribution, and to have nice normalized values between each layer of neuron, we can count how many neurons we have in the previous layer and adjust the weights accordingly, such that the information doesn't blow up or fade out too much between each layer. So that's the detail, but now we get the output. And we had a target, so this is supervised learning. We can compare and evaluate the neural network. By comparing it with an error metric, we can do some math with this metric to adjust every weight in the neural network towards new values of those weights that minimize this error metric we computed. So by minimizing the error metric by changing the weights, the neural network can learn to generate better prediction towards the direction we want it to take when generating predictions. So this is a slow process. We need to do this example after example repeatedly, or we can also accumulate changes in weights for many instances for many examples at once. So we would call this a mini batch. So most of the time when we program deep learning neural networks, we feed in the data using mini batches. We can compare this to a linear regression or a least square regression. It could be called sometimes. This is a technique that can be used to do a linear regression. And notice here that it isn't really a neural network. We're just fitting a line on some points. So this is so just getting back here. This was two-dimensional. We had two inputs. We generated three outputs, and the output was color here, and the inputs were both on the axes. Here we have only one input here below on X, and instead of an output being color, we have an output being a single value here on the y-axis. So this value on the y-axis, which we predict with a linear regression, is just like a linear relationship between the data and what we predict. So with that, we could initialize the linear regression randomly with a random slope and a random offset at the origin here, which is 5 once learned, and we could make it learn on the data to learn to fit. So this is a regression compared to a classification. We predict values rather than classes, which would be picking the max prediction instead of really showing the value of the prediction. But notice that here we have three things. We could have kind of three mountains with predictions of the confidence value of the neurons if we compare them with a z-axis. That would be height here. So the goal is to fit a model from data. So we have an error function to minimize. Here we take simply the mean squared error, also called MSE, and it's the difference of our predictions and the value we expected. And by doing this difference and squaring it, we get a number that is always positive, and it means the difference between the real value we expected and what we predicted here. So we have the distance, and when we square the number, it's always positive. So if the distance was negative here, we square it, and it's back like a positive metric. So the goal would be to minimize the error towards 0, and by minimizing it, we would get the curve, the line to fit. However, here 0 is impossible, as you see, because we simply can't satisfy every point. There still is some error. So a model would be the prediction y is some factor of x plus p. So a is the slope and b is the kind of bias here. It's the offset to origin, and a is the slope which multiply the line. So we could use an iterative learning process. So if we take the error and do the derivative with respect to a, so dE on dA, then this is the slope, the tangent of the error. And this means that if we increase dA, then dE will increase by, if we increase A, then E will increase by that amount. So if we want to reduce the error, then we will subtract a small amount k of this direction, this step we were taking to increase the error. So we decrease the error by moving A towards the inverse direction, which is a small multiplication of itself. And same goes for B. Here it's the derivative of the error with respect to B instead of with respect to A. So same thing goes here. And in a neural network, we would do this for every weight and biases and other learnable constants or parameters in the neural network. So at first, it's initialized most of the time randomly, and we at each training iteration, at each mini batch, we minimize the error a further bit more. So here we have it, the difference of the prediction of the real value and of the prediction we made squared. And when we develop the math, then our neural network is a function of x being our input data, and when we expand the function, this is the neural network. So we have like or sum of things, and this would be in this case a single neuron that is represented. So this is a very simple math. In fact, it can be all automated with auto derivation frameworks. So here with some gradient descent updates, gradient descent, by the way, is the fact of doing this iterative learning process here. So this being the gradient, so the tangent and like the direction we take, so we do descent of the gradient. So it's like if here we have a weight 0 and a weight 1 in a neural network, and we start here, then the loss, which is a synonym word for the error, if we want to minimize it, then we will step in that, if we were here, in that direction. So we would leave the weight 1 untouched, and we would increase a little bit the weight 0, so we would move like that. And example after example, we can see where to move. And notice that normally this is the algorithm is blind, because at every point it moves towards the minimum by minimizing the error, but it doesn't know at every moment what does the rest of the mountain looks like. It's like if there was a bowling ball here and it was downhill. However, we can't. There is fog and we can't see much further around. So we need to look at the data, and the data will tell us where to move. So we do it by mini batches sometimes, because mini batches increase the precision of the direction. If we have only one example we learned from, we might go back because of some weird behavior related to that example or where we were here. But with a few examples, we can be more confident that the direction we take is the good one. Back at non-linearities, I've explained the linear regression, which is also a plane when there is many input x and weights a. So this is the equation of a plane. It's just like the line here, but instead we would have like a 2D plane in a 3D space, with the y here being the prediction and the two x's being inputs, for instance. So if we take the plane of a plane, then doing the math, we end up again with a plane. So conclusion, the plane of a plane is still a plane. So when we stack two neurons, one on top of each other, they would generate just something like the linear regression if they didn't have an activation function which adds some smoothness and some restrictions and some curve in that. So with activation function, or neural network isn't a linear regression anymore. So here's an activation function as promised. Here it varies from 0 to 1 for the outputs, and for the inputs we see that it kind of clamps them. So when we have values near 0, then it moves linearly, but as we get values toward plus infinity or minus infinity, then it has a tendency to clamp them between 0 and 1. So this is the most known activation function probably, and there are a few other ones that are similar. So let's see how to get towards deeper neural architectures.